now.
All right, awesome. Actually, it's all periods, 3 and 4 and 8. This is the snow day. We had no school on Monday, and Tuesday is now Tuesday afternoon, and we're going to do some math, and you're going to watch it, and it's going to be awesome. So first of all, you had homework. If you were in period 4 and 8, you had homework that was due on Monday. If you were in period 3, you had homework that was due Tuesday. Hopefully you did that all already over the weekend, and now you can just get that out right now, and we're going to go over it for like about 10 or 15 minutes. So I thought we could just do a couple of these. Number 85. Also, it's going to be really weird because there's no one here. There's no audience, and I teach by asking BS rhetorical questions to the room, so I can't do that this time.
I can answer those.
Yeah, we have Giles here, is behind the camera, so I'm going to try to do this to an empty room. It's pretty much going to be bad. That's why they tape, like, Saturday Night Live and stuff in front of a live audience. I realize now. All right, so here we go. Number 85. Hopefully this is something that we were doing just at the very, very end of class on Thursday and Friday. Differentiating functions like this, although it looks kind of annoying because there's like multiple product and like chain rules and chain rules inside of product rules inside of chain rules. In fact, it is great. You should be really, really happy whenever anybody asks you to differentiate the natural log of a bunch of stuff, because you can like decompose it all first. So the very smart, essential way to do this is to first apply log rules. So the logarithm of ln of AB is just ln A plus ln of B. So this then be ln of root x squared minus 1, and even that is really just x squared minus 1 to the 1/2, so you can use another log rule, and this becomes 1/2 ln x squared minus 1. That's really great because when you take the derivative of the sum of two functions, it's just the sum of the derivatives. So the more I can split my function up into little pieces, the easier it is to differentiate. So I've done all this work. Now when I take the derivative, it's like really easy. Derivative of ln x is 1 over x, and the derivative of 1/2 ln of something is just 1/2 1 over the something, back inside for the derivative of x squared minus 1, which is 2x. And if you want to write it one final time, nice and pretty, the 2's cancel, so this is 1 over x plus x over x squared minus 1. And maybe you even want to get a common denominator. If so, that ends up being 2x squared minus 1 over x squared minus 1. I think it did that right. X squared minus 1 plus, yep. So that is the derivative. Okay, nice warm-up problem. Anyway, it was an odd, so it should have been in the back. So you should have checked that already. 87 is like another version of the same thing. The function is ln of x over x squared plus 1. So how do we differentiate this? Well, the trick is to first use log rules. So this is ln x minus ln x squared plus 1. And now if I differentiate, it goes a lot smoother. I don't have to use the quotient rule or anything like that. So this is 1 over x minus 1 over x squared plus 1. Back inside 2x. Okay, and then you can simplify if you feel like it. Okay, more. 92. I guess this is just 92 is just another example of this. Maybe we don't need to go over all three of these. Anyway, too late now. So this is ln of the cube root of x minus 2 over x plus 2. This could be rewritten as y equals, well, that's all to the 1/3. So that's really 1/3 ln x minus 2 x plus 2 when you use the log rule and bring down the third. And then this can be even simplified more, so it becomes 1/3 ln of x minus 2 minus ln x plus 2. And don't forget to actually do the differentiation. So this becomes 1/3, and then that is just 1 over x minus 2 minus 1 over x plus 2, and that's it. And then again, you can get a common denominator if you want. The back of the book probably does. Okay, so that was all relatively straightforward stuff. 95, this is a little sneaky problem, which just at first looks just like some kind of silly thing. It's asking for the derivative of the natural log of the absolute value of sine of x. Recall that last class, very, very quickly, we noted that the derivative of the natural log of the absolute value of something is just 1 over x. So this looks pretty easy. So what is this? Well, if the derivative of the natural log of something is 1 over x, and the derivative of the absolute value of sine x is going to be 1 over the something back inside for the derivative of the something. And so this is just cotan. So that's kind of interesting. That's just a weird function, and suddenly its derivative is cotan. So that's cool. Keep that in the back of your mind for much, much later. And there is another problem like this, 98, which was take the natural log of secant x plus tan x, absolute value of secant x plus tan x. Again, we just do it. We take the derivative, and the derivative of ln of something is 1 over the something back inside for the derivative of the something. So the derivative of secant x plus tan x is secant x tan x plus the derivative of tan is secant squared x. You should know all these by now. Okay, however, something magical and amazing happens. If I factor secant out of the top, then I get tan x plus secant x, and in the bottom, I have secant x plus tan x. Whoa! There's no one here for reaction shots.
That's amazing.
That is amazing. Thanks, Giles. In fact, this very strange function, the ln of the absolute value of secant x plus tan x has a derivative of secant. So that's kind of cool, maybe. Put that in the back of your mind also. All right, more. 113. This problem is nothing new, but it is a good example of one of those kind of so-called double chain rule situations. So if y is, this tests how good you are at the chain rule. So y is 37 minus secant cubed 2x. And they want the derivative at 0.36. So basically we're just going to take the derivative and then we're going to plug in 0. That's it. Okay, well, I'm going to take a moment to rewrite this in a derivative-friendly form. Secant cubed 2x is really secant 2x, all of that cubed. So now when I go to take the derivative of this, I have to be very careful. Derivative of 37 is 0, but the derivative of negative something cubed is negative 3 something squared. And then back inside for the derivative of the something. So now I need to be taking the derivative of secant of 2x. And the derivative of secant of 2x also requires the chain rule. So what is the derivative of secant 2x? Well, it's the derivative of secant of something is secant something tan something, and then back inside for the derivative of the something. So I end up with some big thing, which is actually like negative 6 secant to the third 2x tan 2x. That is the derivative in general, I'm pretty sure. Okay, but they want the derivative at 0, so I think I've used this symbol once or twice so far, so it's convenient. This means the derivative evaluated at x equals 0. So this is negative 6 times, well, secant of 0 is 1, and tan of 0 is 0, so this whole thing just becomes 0, I guess. All right, kind of dumb, a little bit of an answer. All right, a couple more. 128. Thought we could do 128. That was, oh wait, not 128 yet. Wait, hold on, what's going on? 123. 123. 123 is the derivative of 4 to the x. Okay, actually, let's pause for a second. Giles, can you flip this around? I'm going to go to the backboard. So, on the whatever day I saw you last, we did this. Like at the very, very end of the period, like as the SRP kids were coming in, we learned how to take the derivative of 4 to the x. Okay, here comes 20-second lecture. We're getting to the point where we have a lot of derivative rules. And it seemed at the beginning that they were very, very easily memorizable because they were just like 3 or 4. But now they're starting to be more like 12 or 15. So here is where opinions will differ. Some students will simply, now that we have more like 25 derivative rules, will just want to blindly memorize all of them. Then you'll have some people who want to memorize as little as possible. You need to find your secret sweet spot, but basically, I do not think that you should memorize how to take the derivative of a to the x. Although on the other hand, I feel like you kind of should memorize it. So this is a little bit conflicting messages. The derivation of this is very, very simple. You should be able to rederive it when you need to. You should be able to take a minute and rederive this. And then eventually, hopefully by doing that a couple times, you should just have it memorized. So how do we do this? Well, we did this exact thing last class. The key is that you need to, I don't know how to take the derivative of a to the x, but I do know how to take the derivative of e to the something. So I want to rewrite, my goal is to rewrite a to the x as e to the something x, which is possible. This is ultimately a change of base formula for exponential functions. And what you do is you take the natural log of both sides. So I write this little equation to myself. I take the natural log of both sides, so I get ln of a to the x equals ln of e to the kx. On the left-hand side, I use a log rule, so this becomes x times ln a. And ln a is just a number. If a should happen to be 4, like in our case, then ln 4 is just some kind of number, a little bit more than 1. ln of e to the kx is just kx. The x's cancel, and so k is ln a. That really only took a couple seconds. What that means is that a to the x can be written as e to the ln of a times x. In other words, every single exponential function is really just a modified e to the x function. And that shouldn't surprise you, because if you think about the exponential functions, they all basically look the same, right? If that's 2 to the x, then 3 to the x is going to look like this. This is kind of stupid to do with no colors, but basically all the exponential functions are like that. They've all just been stretched by some tiny amount. How much have they been stretched by? Well, another way of thinking about of e to the ln a times x is it's just by exponent rules. It would be just no exponent rules. Just leave it like that. I guess it's been
horizontally.
Yeah, it's been like horizontally compressed or something, but maybe that's not worth rewriting. Okay, so yeah. Why is this little formula important? It's because now I'm going to use it to like rewrite this as e to the ln of a times x. And what is the derivative of e to the something? Well, the derivative of e to the something is e to the something back inside for the derivative of the something. And the derivative of ln a times x, well, ln a is just a constant, so the derivative of ln a times x is just ln a. That's just like a number, as if this was like e to the 5x or something. Okay, and then e to the ln x just is a to the x, and that's how you get this formula, which says that the derivative of a to the x is just ln a times a to the x. In other words, the derivative of any exponential function is basically that same exponential function with some constant, which is kind of a brilliant thing already. which says that exponential functions have this property that the rate at which they grow is proportional to themselves. And I think I said this in some classes. Since the ln of e is 1, what's very special about e to the x is that it's sort of constant. The proportional rate at which it grows relative to itself, it happens to be 1. Okay, so this is something which I think you should just do over and over again 3 or 4 times until it makes total sense to you, and then you can just know it by heart, or you can rederive when you need it. Alright, even easier is log base a of x. This is some logarithmic function, but as we know, via the change of base formula, there's really just one logarithm function, natural log. Everything else is just kind of like an imposter. So if we use the change of base formula, log base a of x is really just ln x over ln a. I guess I'm not going to reprove the change of base formula, but maybe you should do that for yourself. So how do you do this? Well, first we just recognize that ln a is just a constant. So this is really just 1 over ln a, that's a number, times ln x. So there's no even chain rule required here. The derivative of a constant times ln x is just that constant times 1 over x. And so that's how you take the derivative of any logarithm function. Okay, this was kind of a waste of 5 minutes because we did this last class, but we did it in a kind of a rushed fashion. So back to this 123, if I'm taking the derivative of 4 to the x, maybe a good thing to do is to just, as you do these problems, instead of using the memorized formula, just go through the logic again. This is e to the ln 4 times x. Oh, even one more step you could do if you want to feel like you really know what you're doing. You could just rewrite 4 to the x as e to the ln of 4 to the x. Yeah, this is good. E and ln are inverse functions, so of course 4 to the x just is e to the ln 4x. And then this is, by x by log rules, this is just the derivative of e to the x times ln 4, bringing down the x. And now we differentiate. The derivative of e to the something is e to the something back inside for the derivative of the something, and the derivative of x ln 4 is just ln 4. And then this part is, as we've seen, just 4 to the x. So that's how I get ln 4 times 4 to the x. Or you could just use the rule that you memorized, but this is sort of going through the logic all over again. All right, a slightly harder problem. Yeah. Did I assign 128? I don't think so. I think I assigned 126. So 126 is y equals x times 6 to the negative 2x. Okay, this is complicated because there's like a product rule, there's like multiple things going on here. So let's just do it. So the derivative of this is going to be derivative of the first, which is just 1, times the second, plus the first. And now I have to differentiate 6 to the negative 2x. Okay, here's where I feel like it's good to just know the formula. So if I just know that the derivative of 6 to the something is ln 6 times 6 to the something. And then back inside for the derivative of the something. So that's that.
No x. No x.
Oh, that's just negative 2, right?
Yes.
Thanks, Giles. Yeah, derivative of negative 2x is just negative 2. Okay, so then we can like clean this up a little bit and make it prettier. So if I factor out the 6 to the negative x, then I get like something, right? I get like 1 minus 2 ln 6x. And usually people put like a times there to make sure that we don't mean ln of 6 times x, we mean 2 ln 6 times x. Or sometimes people even put the x first. Anyway, you could even do more fancy things like pop the 2 up and you could write that as ln 36. But anyway, Looking good. Josh, you approve? Oh, it's good that you're
Yes.
paying attention. So if I mess up somewhere, just
I have a tweak or alternate take on 126.
Oh, you do it
Could you
differently?
use some exponent rules and rewrite 6 to the negative 2x as 1 over 36 to the x?
Oh, he says instead write this as x times just like
6 to the negative second to the x, basically.
yeah. So it's just like 1 over 36 to the x. Yeah, that might be easier. That might be easier. Yeah, that works too. And then you can just do it from there. Okay, more. Let's kind of like try to finish going over this homework. 26. 4 more problems. I'm doing only the ones I think are interesting. Maybe I'm doing even more than you would request. Hopefully, if you had questions, if you had problems, these were the ones you had problems with. 131 is just a very straightforward log base 3 of x. So again, maybe it's a good idea to just, for yourself, rewrite this as ln x over ln 3, which is really just 1 over ln 3 times ln x. I'm essentially like kind of redoing the proof as I do the problem just to strengthen the fact that I actually know what I'm doing. Anyway, then the derivative of this is just constants times the derivative of ln x, which is 1 over x. So I'm just done. 135 is basically just another version of the same thing. So this is log base 5 of the square root of x squared minus 1. So I guess here, the smart thing to do would be, well, there's a lot of different ways to do this. Whenever there's logs, there's tons of different ways. But one thing is, that's really log base 5 of x squared minus 1 to the 1/2. So for starters, I could bring down the 1/2. So I could write this as 1/2 log base 5 of x squared minus 1. And then I guess I could just do it, right? So what is this derivative then? Well, it's 1/2. What's the derivative of log base 5 of something? The derivative of log base 5 of something is 1 over ln 5 times 1 over the something. Back inside for the derivative of the something. That's one way to do it. Okay, 2 more problems I thought we would go over. 154. So 154 says, determine points at which the graph of x over root 2x minus 1 has a horizontal tangent line. So, in other words, take the derivative and figure out when the derivative is 0. Okay, you have a couple options here. You could use the quotient rule, but I think it's much simpler to just, I try to avoid the quotient rule usually unless I have to, and here I definitely don't have to. Because I can write this as x times 2x minus 1 to the negative 1/2. And then writing it like that makes just everything easier in my opinion. So now we take the derivative just using the product rule. Derivative of the first times the second plus the first times the derivative of the second. And what's the derivative of 2x minus 1 to the negative 1/2? It's going to be negative 1/2, 2x minus 1 to the negative 3/2, back inside for the derivative of 2x minus 1, which is 2. Okay, now I think I talked about this in either 1 out of the 3 or 2 out of the 3 classes, but there is, so at this point I do not recommend trying to like throw in all kinds of disgusting like radicals and trying to simplify that way. Instead, let's use exponent rules to their maximum capacity. First off, we can simplify this a little bit. The 2 and the 1/2 cancel. So this is really 2x minus 1 to the negative 1/2. And then it's like minus x, 2x minus 1 to the negative 3/2. So let's just try to factor this. So let's do it. So how should I factor this? Well, they each have a 2x minus 1 in common. The strategy is to factor out the lowest power of 2x minus 1. And negative 3/2 is lower than negative 1/2. That's going to leave you with then positive leftovers. So 2x minus 1 to the this takes some experience, but if 2x minus 1 to the negative 3 halves times 2x minus 1 to the what is going to give me 2x minus 1 to the negative 1 half. Well, that has to be a 1, because when you multiply, you add exponents. So something to the negative 3 halves times something to the 1 is something to the negative 1 half. And then this is just minus x. So this is a really, really fast and efficient way to like do the algebra, which comes up a lot when you have product rules. Now this becomes just x minus 1, and then down here is 2x minus 1 to the 3 halves. So this is a really good way of simplifying your derivative in a fewest kind of number of steps. And then by the way, the problem just solves itself. When is the derivative 0? Answer when x is 1. And I think that was all it asked for, right? Where are the points in which the derivative has a horizontal, or the function has a horizontal tangent line. Function will have a horizontal tangent line when the derivative is 0, and the derivative is 0 at just one number, and x is 1. Okay, last problem I thought we could do was 173. 173 is actually a follow-up of a problem that we had assigned like a couple weeks ago. So maybe some of you already noticed this, but now we're going to actually prove it via the chain rule. And basically, the proof is show that the derivative of an odd function is even, and that the derivative of an even function is odd. Okay, let's just do the first part. So show that the derivative of an odd function is even. So I'll just write derivative of odd function is even. Okay, how can we do this? Well, first we need to recall our definitions of even and odd functions. What does it mean if f is odd? What does that actually mean? Well, it means that f of negative x equals negative f of x. Alternatively, you could write that as just that f of x is negative f of negative x. Those are basically the same thing. That's what it means for f to be odd. What does it mean if f is even? If f is even, then f of negative x equals just f of x. Okay, so if we have these as definitions, I want to take the derivative of an odd function and show that it's even. I'm trying to remember, there's a cool way to do this. I'm not sure if I'm remembering how. I think what I do is, well, let's just start with an arbitrary odd function. So let f of x be odd. If this function is odd, then here is what I know about it. I know, I guess I'll do it this way. I know that f of x is negative f of negative x. Okay, well now let me just differentiate both sides of this. So if I take the derivative of both sides of this function, what I end up with is, well, the derivative of x is f prime of x, and the derivative of negative f of negative x is negative. What is the derivative of f of negative x? Well, chain rule, right? So that's going to be f prime of negative x back inside negative 1. And then I'm just done. Because I've just showed that f prime of x is, the negatives cancel, f prime of negative x. And this is exactly what I wanted to show. That the derivative function has the property that even functions have. Giles?
1 minute.
Oh, perfect. All right, that was 29 minutes. We have finished going over the homework, or the ones I thought were important. Pause for a break, and then we'll do a lesson.